Welcome back everyone. In this lecture we'll learn about various color models, namely RGB, CMY and HSI color models. So let's learn about the concept of color models, why we need them. The color models are also called as a color space or color system. The purpose of a color model is to facilitate a specification of colors in some standard, generally accepted way. We can have RGB color model for monitors or video camera, and we can have the CMY color model which is cyan, magenta and yellow for color printing. Also we can have CMY and black along with the CMY colors. We'll get back to that later in the topic. And we can also have the HSI model, which corresponds closely with the way we humans describe and interpret the color. So we'll take a look at these three models in depth. Let's look at the first color model, which is the RGB model. And the RGB color space is related to human vision through the tri-stimulus theory of color vision that we looked at in the previous lecture. And the RGB is an additive color model. The primary colors red, green and blue are combined to reproduce other colors. In this color space, a color is represented by a triplet, mainly RGB in this format. And here R gives the intensity of the red component, G gives the intensity of the green component, and B gives the intensity of the blue component. And here we assume that RGB are real numbers in the interval 0 to 1. And you will often see values of RGB as integers in the interval 0 to 255. So you can either normalize this range 0 to 255 to be between 0 to 1. So uh, any uh, any format we can use which is suitable for our interpretation. So normally for a 8-bit image, we usually represent values of R, G and B between 0 to 255. So what we mean by this additive color model? Uh, we have seen the television or the projector. So basically, these are the active displays, and these active displays, such as computer monitors and television sets, emit combination of red, green, and blue light. And this is an additive color model. So, as we have seen in the previous lecture, adding red, green, and blue in high intensity produces white light. So that's why we call it as additive color model. So this is the Cartesian coordinate system representation for RGB color spaces, and you can see we are representing each color along the X, Y and Z direction, and when all the values are 0, they produce black color. So black is represented as 0, 0, 0. And if you make them high in intensity, means maximum value for each component RGB, so it produces white, so it is 1 1 1. Okay, so the solid diagonal represents the grayscale values, and if the value of red is 1 and green is 1 and blue component is absent, that is represented by 110, we'll get yellow color. And similarly, if we have blue and red components and absence of green, that will produce magenta. And similarly, if there is a absence of red and presence of high intensities of green and blue, we'll get cyan color. And this is the 3D representation. and we'll have a similar representation for the CMY model also, and HSI model in later slides. This is a cube that we get when we color the coordinate system that we saw in the previous slide. So this is the red plane, the green plane, and the blue plane, and these are the hidden faces. So this is the blue intersection of blue and green, where red component is 0, and here the green component is 0. That means it is the red and the blue plane, where we have this magenta, and here the blue component missing, so we have the yellow here at the corner. So in the color cube or in RGB color space, if you represent 8 bits per color sample, like 8 bits for red, green, and blue, you will get 24 bits in total, and that corresponds to 2 raised to 24 bits, that is 16 million colors. So that is what you get on a regular mobile screen or a television display, uh, the LED TVs that we get these days. So the LED TVs or the mobile screens or any display system that we see basically works like this. It has a red, green, and blue components. When they are merged, we get the RGB color, full RGB color. So when we take the red component out, green component out, and the blue component out, and view them individually, they basically appear like a grayscale images. Only when we stack them one over the other at the place, we get a full color image. Most modern computer monitors or televisions and the mobile displays can transmit true color. That means 24-bit color. This means each channel contains 8 bits per channel that can transmit color, so as we saw in the previous slide. And 8-bit means the channel can make 8 combinations of on or off of the color per pixel, 256 colors total. You have basically 3 channels for RGB, and each channel is basically having 256 different shades or colors. Now, totally, how many colors can be generated with this is 256 into 256 into 256, which is 17 million 777 to 16 colors. So this is 16 million colors approximately. That is basically 2 raised to 24. So this is the case for all the modern computers and televisions. Also, we can have 8-bit colors, 8 bits per pixel. It means only 256 total colors. And these are called as web safe colors because they are sure to render accurately on anyone's monitor. So this is a 8-bit uh, color, and this is a 24-bit color. And for the smaller image, the differences are hard to identify. And nowadays, with the power, with the computing power that we have, and the storage available, and the bandwidth we are getting, we rarely go for the 8-bit colors. But nonetheless, it is there with all the operating systems as a standard. So these are called as basically safe RGB colors. So these are 216 colors common in most operating systems, and these are the all the gray in the 256 color RGB system. Okay, so this is how the color plane looks like. All the 6 faces of the color cube looks like in a safe color environment. And when you turn on the PC in the safe mode, this is basically what's happening. You won't get all the 16 million colors. You'll end up with these many colors, maximum of 256. And this is the color cube for 8-bit colors. So RGB cube is divided into 6 intervals on each axis to achieve a total of 6 raised to 3, which is 216 common colors. And however, for 8-bit color representation, there are total of 256 colors. Therefore, the remaining 40 colors are left to the operating system to define. And these are the color equivalents, which is valid values of each RGB component in a safe color environment. Next is the CMY color model. We need the CMY color model because additive color won't work for printing purposes, because in printing we don't begin with black. As we have on this monitor, this background is black, and by adding RGB we get white light. But on a printing surface, the paper is typically white, and that means the light and all the colors are already present, and we need to subtract them from the background. So basically we must begin with a piece of paper, and that's usually white. And white, as we know, is all colors, so we can't add to all colors, we must subtract. Furthermore, an offset printing press can generate the enormous number of colors available on a computer screen. As we saw in the color gamut theory, the printing or the displays and the televisions or the projectors can generate more number of colors compared to a printer, because printer you need to deal with the ink, and inks you need to come with the, you need to think about mixing the inks, the pigments, so you won't get the range that you can get in the displays. And we need to run a piece of paper through the press for each ink. That was the case in previous generation printers. To get a color image, uh, we had to pass the paper thrice for a full color image. So this is the example for CMY color printing. So as you can see, the background is white, and in order to get this image, we need to put cyan ink first, and then the magenta, and then the yellow. And additionally, we can also use a black ink. We'll come to this topic later in a while. Okay, why we need this additional black. So all in all, three color pigments added together will generate a full color image. So the printing is basically based on the subtractive color system, and you can actually project the additive colors to produce the subtractive colors like this. So we have the RGB, and when they combine, you can see the secondary colors here, or the subtractive colors. So here is the cyan, magenta, and the yellow, and in between we have the white color. In order to convert from CMY to RGB, we can simply use this equation. So it's 1 minus RGB. Straight away we'll get the CMY representation from the RGB. And this is the uh, CMY color wheel: yellow, magenta, and cyan. When they combine in equal proportion, we get black. And between yellow and cyan, we get green. Between yellow and magenta, when they merge, we get red. And magenta and cyan produce blue. And see, this relationship uh, is true in all color models that we are studying. So that means between yellow and magenta is red. In other way, what we can think is between red and green is yellow, between green and blue is cyan, and between red and blue is magenta. So this relationship between the colors will hold true in all color models. Let us visualize the working of a CMY color model. So we can think about the pigments as something which absorbs light, and we can think that they are the color filters. So you can see the magenta acts as a green light filter, means it allows red and blue to pass through by blocking green, and yellow blocks blue light. It allows only red and green to pass through, and cyan blocks red color and allows green and blue to pass through. Now, if you put magenta and yellow together, it will block green and blue and only pass red color. And similarly, what happens when you put yellow plus cyan. So answer is here. Yellow plus cyan will block red and blue. It will only allow green light to pass through. And similarly, if you put the cyan and magenta, it will only pass blue light. Remaining colors will be blocked out. So this is how to think about CMY color model. So these are the three color cartridges used in the color printers, CMY. So when you put all three inks uh, on a paper, it will produce black, and if you don't put anything, it will remain white. So and any other combination you can create by mixing the colors in right proportion. So this is the CMY color model based on the Cartesian coordinate system, and we are representing the three colors on the three coordinates. And the major difference with the RGB model that we studied earlier is that the origin is white here, because the base that we are printing is usually white. Okay, so white is 0 0 0, and as you put uh, uh, equal amounts of CMY, you get this grayscale line, and when you put them in maximum intensity, you get this pitch black. Okay, so this solid diagonal is the grayscale line, and if you put only cyan and don't put any other color, you will get only cyan uh, color as printout. And if you add cyan and magenta, you get a blue color, and if you add cyan and yellow, you get green, and if you add yellow and magenta, you get red. So this is the color cube in the CMY color space. The conversion from RGB to CMY is given by the formula. CMY is equal to 1 minus RGB. Very simple and straightforward conversion. So the red color is written in RGB as 100. In CMY, it is written as, uh, so use the formula CMY is equal to 1 minus RGB, which is equal to 111 minus 100. So basically it's a 0 1 1. So 0 is for cyan, and 1 for magenta, and 1 for yellow. So that is the magenta and yellow. CMY color model may not always produce desired results. That is because when we add CMY in equal proportion, we expect to get black, but in reality that black is not pitch black. It will be somewhat muddy. You can see here in this region, in the background and in the foreground also, in some parts, the black isn't well defined. It looks muddy, but in the bottom image, the black is clear. Okay, and it adds to contrast part, and this is the difference here. So what we do here is we are adding a extra tone, which is black, and we call it as key color. Okay, so that's why we call this model as CMYK model. uh, we won't use B for black here, because B is already taken by the blue color, so we'll call it as K as key color. Okay, so that is the use of having CMYK color model. So the image on the left was printed with only CMY inks. Black ink basically adds contrast and depth to the image on the right. So this is a typical CMYK color model, color printer, and the reason for using black is like these yellow, magenta, and cyan colors. When they are added on top of each other, it's basically ink, so it will take some time to dry, and also they will not generate the black as we desire. It will look muddy. So instead, we'll just add some black ink. it will give some vibrancy to the printed image. Next type of color model we are going to study is the HSI color model. Now, why we need this type of color model is because humans do not describe any object uh, using RGB or CMY color model. For example, if you see an apple, you won't say that it is 70% red, 20% yellow, 10% blue. No, that is not how we humans describe any color. How we describe color is by its hue, saturation, and brightness. And HSI color model mimics the way we humans interpret the color. So, hue is the color attribute. That means it is whether it's red, green, blue, yellow, cyan, indigo, whatever color it is having. And saturation is the purity of that color. It is a purely red or light red or dark red. That is given by this saturation component, which we already studied in the introduction part. And then the brightness, which is a chromatic notion of the intensity, how much intense that particular object is. Maybe it is a self-illuminating object or it is a reflecting. So how much intense that particular object is. Now the biggest reason for using the HSI color model is that in order to enhance the image, we just have to operate on the I component, which is the intensity component, which will give us the desired results. In contrast, in RGB and CMY color model, we need to operate on all the components. That means we need to operate on R plane, G plane, and B plane separately to get the desired results. But in HSI, we'll just keep the H and S component aside, and we'll operate only on the I component, increasing the contrast or any other manipulation, and the result will be similar to the one we see on operating on RGB component. So that is the major advantage of going for HSI color model. So RGB and CMY models are not good for human interpretation. So and in HSI color model, hue and saturation gives the color carrying information and intensity gives the brightness. This is the summary of the things that we learned in the previous slide. So hue means a dominant wavelength and saturation is the purity of that particular hue, and then intensity or the brightness of that particular strip from dark to full bright. Now let us understand the relationship between RGB and HSI color model. So this is the color cube, and as you can see, the relationship between the colors remain same. So between blue and red you get magenta, and between red and green you get yellow, and between green and blue you get cyan. So that relationship will always hold. Okay, so no matter which model you are using, when you mix blue and green you will always get cyan, and green and red will always generate yellow. Okay, now how to translate this information into HSI model? So we'll concentrate on this red line. So blue, green, red, all are there, and then we have yellow, magenta, and cyan. So additive primaries and subtractive primaries both are there on this red line. Now we you turn this into a circle. Okay, then the relationship will remain the same. So we have blue here and green here. In between blue and green we get cyan, and between green and red we get yellow, and between red and blue we get magenta. Next, if you extend it into three-dimensional space, as you increase the brightness you get white, as you decrease the brightness you get black. And observe one thing here, as you increase or decrease the brightness, the area of this red circle decreases. Okay, so it is optimum or it is maximum only at this maximum mid level. Okay, and here is the saturation. As you move away, you get saturated color, and this is the angle. Hue is the angle. Now, if you increase the brightness, the area of the circle reduces. That means the number of colors that you get will reduce as you increase or decrease the brightness. Because if you have observed on your television, if you go on increasing the brightness, uh, the brighter colors will start becoming whiter and whiter, so you will end up with all white colors. And if you decrease the brightness, the darker colors will get black, and more colors will get darker and darker, and ultimately becoming black. So that means only at this optimum level you get maximum color representation. So if you increase or decrease the brightness, you will lose out on the color details. So this is the HSI color cube, color representation in 3 dimensions. This is the color cube. So basically the hue is defined as an angle in HSI color space, where 0 degrees is red, 120 degrees is green, and 240 degrees is blue. And again 360 or 0 degrees will be again red. And saturation is defined as the percentage of distance from the center of the HSI triangle to the pyramid surface. And its value ranges from 0 to 1. And intensity is denoted as the distance up the axis from black. Okay, so at the midpoint you will get maximum color representation. As you go further, it will become whiter, and if you stay at the lower axis, it will be darker image. So these are the various representations for hue and saturation in HSI color model. So you can go for hexagonal representation, where you have all the colors represented on a corner, on each corner, and the white is in the middle. And you can also have a circular or triangular representation. So in all these things, you can note that the relationship between the colors remains same. Like between green and blue you have cyan, between green and red you have yellow, and between red and blue you have magenta. So basically a dot in the plane is an arbitrary color. Hue is an angle from the red axis, and saturation is a distance to the point. So this is the actual color representation of HSI color model, and as you can see, this color wheel is bigger in this mid portion, and as you increase the brightness, we have this smaller area circle with these many colors. So the colors that we can create will depend on the intensity. So if you keep it at the optimum level, you will get maximum color representation. As you increase or decrease, you will get less number of colors being generated. So this is the RGB color cube, and here we'll see the HSI components of RGB color cube. So here we have the hue component and the saturation. Note that this part is black here because it's white in the color cube. So this point will be pure white, and there we won't see any kind of color. So in saturation part, this is black. It looks black because no color is present, and at the edges you can see it's full white. So intensity is high in saturation, means it's pure color. Okay, so these are the pure colors on the edge, and these things are represented by white color. And then intensity, this is the intensity map. Again, intensity is more at this corner because it is pure white, and when we have RGB color at maximum value, we have white color, and the intensity will be more at this point. Now let us see how to convert from RGB to HSI. So hue is basically an angle. So hue is equal to theta if B is less than or equal to G, else it will be 360 minus theta if B is greater than G. and theta is equal to cos inverse of half into r minus g plus r minus b whole divided by r minus g whole square plus r minus b into g minus b whole raised to 1 by 2, which is basically square root of the denominator term. Next, s is equal to 1 minus 3 by r plus g plus b. So using this formula, we can convert any RGB value into HSI. So for I is equal to 1 by 3 into r plus g plus b. So this completes the RGB to HSI conversion. Now let us see how to convert from HSI to RGB. So here we need to first check which sector that color is falling. So basically if it is in RG sector, that means the H value, the angle of H is between 0 to 120 degrees. Then R is given as I into 1 plus S into cos H divided by cos of 60 degree minus H. And B is equal to I into 1 minus S, and G is equal to 1 minus R plus B. So this will give the RGB representation for RG sector. And next for BR sector, which is H value falling between 240 to 360 degrees, H is equal to H minus 240, and B is equal to I into 1 plus S cos H by cos 60 degree minus H. G is equal to I into 1 minus S, and R is equal to 1 minus G plus B. So this is for the BR sector, and last sector is GB sector, which is 120 to 240 degrees of H, and for this H is equal to H minus 120, and R is equal to I into 1 minus S, and G is equal to I into 1 plus S into cos H by cos 60 degree minus H, and B is equal to 1 minus R plus G. One way to remember these equations is to note that the RGB terms are cyclically interchanging their position, and the RHS part essentially remains the same in all equations. So just know, or just try to evaluate the uh, cyclic nature of their appearance on the LHS. Okay, and that will be easy for you to remember. In this lecture, we have looked at various color models like RGB, CMY, and HSI color model. And in the next lecture, we'll learn about pseudo color image processing. See you at the next lecture. Thank you.